Bismillahirrahmanirrahim. Assalamu alaikum. Welcome to the online data structure class. What we will be doing today is to start the third online lecture on chapter 7, which is on sorting. In order to find the recurrence equation for the number of operations of merge sort, it will be a function of number n data elements that needs to be sorted. So let that function t of n be running time of merge sort on an input of size n. Merge sort works by splitting the array into two subarrays, which is the divide phase that takes time order complexity of 1. It's a constant. Now, two subarrays, each about half the size of the original array, merge sort will sort the subarrays as well. The time it takes to sort two subarrays, each of size n by 2, is 2 times t of n by 2. Then the subarrays, after being sorted, are merged. The cost of merging two subarrays, each of size n by 2, equals order constant times n, where the constant c is usually taken as 1. For recurrence equation, total running time t of n equals t of n by 2, which is the left half, plus t of n by 2, which is the right half, plus n, which is merge operation. So which equals 2 times t of n by 2 plus n. Now t of 1 equals 1, which is our base case, and it implies the cost of merging single element arrays. We will usually ignore the base case, assuming it's always a constant. You can have t of 1 equals to c, where the constant c equals 1. The non-linear recurrence relation can be solved by using the telescopic method. We take the recurrence relation equation, which is t of n equals 2 times t of n by 2 plus n, and divide both sides by n such that we get t of n divided by n equals 2 times t of n by 2 divided by n plus n divided by n, which equals 1. Now the equation is valid for any n which is powers of 2. We can write the equation in the following form: t of n divided by n equals t of n divided by 2 divided by n by 2 plus 1. Now dividing n by 2, we get t of n by 2 divided by n by 2 equals t of n by 4 divided by n by 4 plus 1. Now again we divide n by 2, we get t of n by 4 divided by n by 4 equals to t of n by 8 divided by n by 8 plus 1. So if we keep on dividing n by 2, we observe the following pattern as t of n divided by n by 2 divided by n by n by 2 equals t of n by n divided by n by n plus 1. Now if we simplify, we get t of 2 divided by 2, which equals t of 1 divided by 1 plus 1. When we sum all the left hand and right hand sides, all of the other terms cancel and we are left with log n equations. All the number 1's at the end of the equations add up to log n. Thus we get t of n divided by n equals t of 1 divided by 1 plus log base 2 n. Now multiplying both sides by n, we get t of n equals n log base 2 n plus n, which basically equals order n log n. Another way to solve the recurrence relation is by the substitution method. We know that t of 1 equals to 1 if we can substitute t of 1 into the right hand side of t of n, we can solve the recurrence. Now let's substitute the recurrence relation continually on the right hand side. T of n equals 2 times t of n by 2 plus n, and let it be equation 1. Now let's substitute n by 2 in equation 1. We get t of n by 2 equals 2 times t of n by 2 to the power 2 plus n by 2. Let it be equation 2. Now let's substitute n by 2 to the power 2 in equation 1. We get t of n by 2 to the power 2 equals 2 times t of n divided by 2 to the power 3 plus n by 2 to the power 2. Let it be equation 3. Now let's substitute equation 2 into 1 and we get t of n equals 2 times t of n by 2 to the power 2 plus n by 2 plus n. Let's simplify. So we get t of n equals 2 to the power 2 times t of n divided by 2 to the power 2 plus 2n. And let it be equation 4. Now if we substitute equation 3 into 4 and simplify it, we get t of n equals to 2 to the power 3 times t of n divided by 2 to the power 3 plus 3n, and let it be equation 5. Now if we keep on substituting, we will observe the following pattern. T of n equals 2 to the power k times t of n divided by 2 to the power k plus k times n. Now since n equals to 2 to the power k, if we apply log base 2 on both sides, log base 2 of n equals to log base 2 of 2 to the power k, then we can get k equals to log base 2 of n. Now if we substitute the value of k into the observed pattern we got and simplify the equation, we will be ending with t of n equals to n log n. The next technique that I will discuss is quicksort. Quicksort, although it uses divide and conquer strategy, but does not require order n extra spaces that Mergesort requires when merging two subarrays. It is the fastest known comparison-based sorting algorithm in practice. As mentioned earlier, Quicksort uses divide and conquer approach, on average it has time complexity of order n log n. Although its worst case time complexity is order n squared, but the worst case seldom happens. In order to understand the basics of the quicksort algorithm, let's take an array S to be sorted. If the size of the array is less than 1, then you simply return and do not do any computation, as it implies the array is sorted. If the size of the array S is greater than 1, then you pick any element V in the array S as the pivot, such that the array S is portioned into two groups, left subarray S1 and right subarray S2. The elements in the left subarray S1 are all less than pivot, and the elements in the right subarray S2 are all greater than the pivot. Ideally, the median value of the array needs to be the pivot. We can rearrange the array such that the pivot is in the median spot. Then recursively sort left and right subarrays. Then concatenate left and right subarrays in order 1 time complexity. Then, here in the pictorial example, the first step taken for quicksort algorithm is to select a pivot. The pool of numbers that we would like to sort contains 13, 81, 92, 43, 65, 31, 57, 26, 75, and 0 in the array. We would like to pick the pivot such that our portioned subarrays are as close to equal in size as possible. Here we have randomly selected number 65 from the array as our pivot. The element to the left of the pivot, which are 13, 0, 26, 43, 57, and 31, are less than the pivot, and the elements to the right of the pivot, that are 92, 75, and 81, are all larger than the pivot. Now we will recursively sort the left subarray, which contains elements that are less than pivot, and right subarray, which contains elements that are greater than the pivot, until all the elements are sorted. Then merge the two subarrays to get the full sorted array. We would like to pick the pivot such that our portioned subarrays are as close to equal in size as possible. A wrong way of picking the pivot will be to use the first element in the array as the pivot. If the array is pre-sorted or in reverse order, then all elements go to left subarray S1 or to the right subarray S2. The pivot in this case is providing a poor partitioning. Sorting the elements to the left or right subarray will take order n squared time complexity to do practically nothing if the array is pre-sorted or in reverse order. First element pivot choice is viable if the array contains random numbers. Quicksort will take order n squared time to basically do nothing. A safe maneuver would be to choose a pivot randomly, for which you need a random number generator, which is expensive because it will only add cost, increase and not decrease the average running time of the overall algorithm. Ideally, the pivot should be the median of input array S. The median is basically an element in the middle of the sorted sequence. Unfortunately, it does not make sense to sort the array in order to calculate the median in order to use it as a pivot. So to find the approximate median, we can instead compare just three elements of our subarray: the first, the last, and the middle. By this manner, you can get the median of the leftmost and the rightmost, as well as the middle element of the array S. Thus take the median value of these three as pivot. In order to better understand Quicksort, let's take a look at an example. Let an array or list S equals 6, 1, 4, 9, 0, 3, 5, 2, 7, and 8. For sorted array S, the leftmost value will be 0, and for unsorted array S, the leftmost value will be 6. Similarly, for sorted array, the rightmost value will be 9, and for unsorted array, the rightmost value will be 8. Center of sorted array equals 9 by 2, taking the floor value, which equals 4. Whereas for unsorted array S, the center value equals 0. Our choice for the pivot will be then taking the median of the three values we have in array S: leftmost, which is 6, rightmost, which is 8, and the middle, which is 0, and picking the median value, which comes out 6, as our pivot. Once we have our pivot, we take the original array input as, and the first thing we do is take the pivot out of the way by swapping it with the last element, such that number 8 and 6 get their positions swapped. Then we introduce two indices, I and j, basically which constitutes a loop. I starts at first element and moves forward. J starts at next to last element, basically avoids the pivot and moves backwards. If we look into the looping aspect of the algorithm, while I is less than j, we move I to the right till we find a number greater than the pivot. We move j to the left till we find a number smaller than the pivot. Now, if I is less than j, we swap the two values at index I and j. The rationale here is to push larger elements to the right and smaller elements to the left. At the end, we swap the pivot with array index I. Inside the while loop, index I will iterate over elements from left to right and search for element that is greater than pivot. Index j will iterate over the elements from right to left and search for the elements that is less than the pivot. The first element of index I is 8, which is greater than the pivot, and it will be grabbed for swapping. Index j, first element, is 7, which is greater than 6. Index j will increment to the next element, which is 2. Since 2 is less than 6, it will be swapped by 8. 8 takes the place of 2, and 2 takes the place of 8. Index I now will increment to second element 1. Since 1 is less than 6, it will again increment to element 4. Element 4 is less than pivot. Index I will again increment to element 9. Since 9 is greater than pivot, it will be grabbed for swapping. For index j, the third element is 5, which is less than the pivot, and the swap occurs with 9. Index I will increment to element 0. Since it's less than 6, it will again increment to element 3, which is less than 6. It will again increment to element 9. Since it's larger than 6, it will be grabbed for swapping. Index j will increment to element 3. Since it's less than 3, it will not be grabbed, and no swap will occur, since indices I and j have crossed each other. The only swap with index I that will occur is with the pivot element. Pivot element 6 takes the position of 9, and 9 takes the position of 6. We need to remember one thing here is that this algorithm occurs over and over the same way recursively until the array is completely sorted. It happens to each new subarray that is created. For small arrays, array size less than or equal to 20, insertion sort is faster than quicksort, since quicksort has too much overhead for small array sizes. For homework assignment, go through the source code of quicksort, the code available in your book as well as in your lab. For homework submission, I would like you to repeat the shell sort example in the lecture slides, where we did the array containing 81, 94 up to 15, and we used shell sort increment 531. Would like you to use Hibbert's increment to sort this example. The next homework assignment will be from heap sort, the example we did in the lecture slides for your array 46, 52 all the way to 95. We built a max heap, but I would like you to build me a min heap and perform delete min operation. So that's your second question. The third is on merge sort. Just sort the following unsorted array. You have 16, 12, 14, 10 up to 13. The fourth is quicksort. You have the unsorted array 14, 15, 12 up to 11, and use the first pivot as 11. Okay, so these are the 4 questions that I would like you to do and submit.